Okay, ladies and gentlemen, I am back, and we're going to look at some other things to help us out. All those sines and cosines can get very laborious, so we want a simpler notation, if you will. You got to use complex variables for that and use Euler's identity. Once you get used to this, it's a bit like the metric system. It works a lot better, cheaper, and faster, but takes a little getting used to. Thinking of an exponential with a complex exponent. So we take our excitations here. We can write a response is going to be this sum of the angles. For a sinusoidal excitation, you have the sine function and the same frequency with a phase angle. Different amplitude. The amplitudes change. So we multiply the sine portions by j, and we get this identity. Vm e to the j omega t. So the imaginary part takes care of the sines, real part takes care of is in the cosines. And we can have the response similarly can be rewritten like so. And then we can also, this will factor out. When we make equations, this will factor out. Actually, it's when you look at the magnitude, when you look at the amplitude, you can write it like this. The leading factor. Where's the leading factor? This factor right here. You can write it like this instead. Okay, so let's look at our previous example. And these are some going back between complex and our regular notation. We have these identities. They're kind of a note on the side. We have our excitation. We have the form of the solution for the current going through here. And we write down our KVL equations just like before, differentiate the I, and put everything together. So L d I dt is given by this, R I is given by this, and we have some reduction to do. We can take the Im e to the j omega t, this stuff here, gather it up. It's a common factor, and so we have j omega L plus R right there. And then this itself can be broken down into the multiplication of two factors. Equate it to the right hand side over here, and we have this equation. This is what I mean by the e to the j omega t factors out. We divide both sides of the equation by e to the j omega t. So we have this, that Vm has to equal Im e to the j theta times this multiplying factor out front. Rearranging this, we get this. And the purpose of doing this, we're going to multiply both the top and the bottom by the this factor right here. The purpose for doing that is so that we eliminate complex numbers in the denominator. Because we notice when we do multiply this by these two by each other, that you're going to get r squared plus omega squared L squared on the bottom. Okay, and then of course this on the top. VMR is the real part, which has to equal Im cosine phi. negative omega L is the imaginary part, and that has to equal Im sine of the phase angle. This is just expressing the numerator as a magnitude and a phase angle. So, gathering everything up all together, we can, substitute this right here. And of course this stays alone, and we get this. So we have the VM term, and then the reason why this is in the denominator, you'll notice, I might as well write down the equation right here. Root ink going. Now, the equation then becomes VM times root, I'm just making the substitution, this into here, making this, substituting this in for this. And that just ends this little down thing just ends the square root symbol. E to the, did they forget a J here? That's the phase angle, so you need a J right there. Minus J, and I'll call it, oh, should I call it phi? Yeah, that's fine. Okay. So that's this. And they're using they're saying e to the j phi equals tangent of negative j tan. This expression is phi, the negative, including the negative sign, is phi, by the way. That's the way they're doing it, so I need to be more careful with my positives and negatives. Okay. Close, that's the numerator. The denominator then becomes, well, the denominator is still r squared plus omega squared L squared. And this is root r squared plus omega squared L squared. So you change it like so, and voila, you have what they wrote down. And again, a J is missing here. Okay. It's good to work through this just to see how everything works. It jumps. These slides sometimes jump from one equation to the next, and I like to kind of go through the process to show you the process. I don't know if you guys have noticed it, but I use the tell, show, do, apply method of teaching. In other words, I tell you what's going on, I give you an example, and then turn you guys loose for you to do it so you can practice. This has the meaning that the source voltage is the real part of this imaginary number, The current is the real part of the imaginary solution that we came up with. So here's the IMJ phi, and of course we need to multiply back to the e to the j omega t. There we go. Remember this factored out when we were working with things? So we put that back in at this point and express things as they should. And it's identical to what we got before. Okay. Next topic, stopping here. Next topic will be phasors.